Hey everyone, and welcome to 12.4, the cross product. So what we're going to talk about today is another way of multiplying matrices, but this time what we're going to be doing with the multiplying matrices is that after, we multiply our matrices, we're actually going to get a vector. And so instead of producing a scalar like the dot product does, the cross product is going to give us another vector. And the vector that we're going to have for this case is going to be a vector that's going to be orthogonal to the two vectors that we use for the cross product. Now, when we're finding the cross product, we're going to denote that A cross B. And we're going to get three components or two components, whatever type of vector. If we're doing a component vector, we're going to get two vectors as the resulting of the cross product. And the same thing if we have three. And so we're just going to match them all up, all of our first components, second components, and third components. And we're going to, in order to find the first component, what we're going to do is we're going to find the determinant using the last two. So that's how I have I multiplying the last two components of each j and k. And then if I want to find j, then I'm going to multiply the first and the third components. And then if I want to find k, I'm going to find the components of the first two. And so that's pretty much how we set this up. That's how I have all these kind of matrices set up. And in order to solve, we're just going to find the determinant. If you don't remember what the determinant is, it's basically just the cross product, the difference of the cross products of our matrices that are in that are part of each component. And so it should not be too difficult as we go through this. So let's talk a little bit more about what we're going to get when we multiply these two vectors. So the vector A cross B is orthogonal to both A and B. If A and B are represented by directed line segments with the same initial point, then the cross product A cross B points in a direction perpendicular to the plane through A and B. That the difference of A and B is given by the right-hand rule. If the fingers of your right hand curl in the direction of a rotation through an angle less than 180 degrees from A to B, then your thumb points in the direction of A cross B. And we'll explain that, especially when we go over the second page, and I'll try to highlight that before we start on the videos. So basically, this is what we'll get. We'll have two vectors. Say here's vector A, here's vector B. And the cross product is going to be a vector that is going to be perpendicular to those. In one direction. So that could be A cross B. And then we could also have another vector going down that's also going to be orthogonal. But then that could be B dot A. All right. It could be reversed, going down could be A cross B, and going up would be B cross A. It just depends on what's the resulting vector. So part of this is trying to figure out, okay, does our cross product, is it, point up or is it point down? And so we'll be able to discuss that, and it has to go between a certain angle measure for us to figure that out. All right, so now let's just go ahead and try to do the cross product. And so we're going to go ahead and start with vector A and vector B. And we just want to find the cross product, and then we want to verify it to make sure that it is orthogonal to both A and B. And so we'll go ahead and start. So our vector A, again, if you wanted to know A as 0, 1, 7, and vector B as 2, negative 1, 4, go ahead. It doesn't matter. You don't have to put this in standard basis form, all right? So if you want to just look at it through that, those two vectors, that's fine. And so now we're going to do A cross B, and I'm going to use this, this standard basis form. And so in order to find A cross B, what we're going to do is I'm going to go ahead and set everything up. So I have I, J, K, and then I have 0, 1, 7, and I have 2, negative 1, 4. And so what I'm going to be doing is I'm going to be finding the cross product. So since I want to do I first, I'm going to take the second components of each, and I'll have 1, 7, negative 1, 4 times I minus, so now I'm trying to find the second column, so the second component, so I'm going to do 0, 7, 2, 4 times, or not times, but component J, and then for component K, the last part's going to be plus, and then I have 0, 1, 2, negative 1, K. And so now, what we're going to do is we're going to find the determinant. So to find the first value, what we're basically doing is we're going to multiply across. That's one of the reasons why I call it cross product. So we're going to multiply 1 times 4 and then minus 7 times negative 1. So that's finding the determinant. It's going to be the difference. So I'm going to have 1 times 4 minus 7 times negative 1. And that's going to be my component I. Minus, again, 0 times 4 I don't know why I did that. Minus 7 times 2. J plus, again, cross product, 0 times negative 1 minus 1 times 2. Okay. And so my resulting vector is going to be 4. 7 times negative 1 is minus 7, so it's 4 plus 7, so I'm going to get 11 for that first vector. Or not, first component, 11i. And then 0 times 4 is 0, minus 14, so minus a negative 14, so plus 14j. And then I have 0 times negative, so 0 minus 2, so just 2, so plus 2. I'm sorry, minus 2. Okay. All right, and so there's my cross product. And then what I want to do is I want to verify that it is orthogonal to A and B. And maybe you can remember from last class how to make sure that something's orthogonal. All you're going to do is you're going to take the dot product of the two. So let's go ahead and take the dot product. So take the dot product of A with and I don't know why I put the magnitude there. Should not have put that there. So A dot A vector cross B vector. So the cross product of A and B times the A vector, or the dot product of the A vector. And so we're going to get 0 times 11 plus 1 times 14, and then plus 7 times negative 2. And if this is 0, then it works out. So 0 plus 14 minus 14 equals 0. So yes, it is orthogonal to A, and to save some time, it's also going to be orthogonal with B. All right, just go ahead and make sure. So the next one is an example. Show that A cross A is always going to give us the 0 vector. So if ever I'm taking the cross product of a vector of itself, I should always get the 0 vector. So I'm just going to briefly show that. And so I'm going to say the A vector is A sub 1 and A sub 2. I'll just do A sub 3. And again, you can skip through this if you'd like to, because I'm just showing a little proof. And now, if I want to do the cross product of A, then what I'm going to get is I, J, K, A sub 1, A sub 2, A sub 3, A sub 1, A sub 2, A sub 3. And I'm just going to go ahead and set everything up. And so I'm going to go ahead and do the cross product. So for I, I'm going to cross A sub 2 and A sub 3 and A sub 2 and A sub 3. And so I'm going to get A sub 2 times A sub 3 minus A sub 3 times A sub 2. I minus, now that I'm finding J, A sub 1 times A sub 3, A sub 3 times A sub 1. First time this has ever happened. Alright, so A sub 1 times A sub 3 minus A sub 3 times A sub 1, K. Nope, not K, but J. Plus, and then A sub 3 times A sub 2 A sub 1 times A sub 2 minus A sub 2 times A sub 1, K. And here you see I get 0, I, minus or plus 0, J, plus 0, K. So therefore, yes, I do get the 0 vector. 0, 0, 0.